You can't do the interesting things that Ethereum wants to do without allowing open-ended computation. You don't want to do the interesting things that Ethereum wants to do in Bitcoin because you don't want to allow the additional computational complexity.
Hey folks, on today's episode of Speaking of Bitcoin, we'll dig into a critical topic in the blockchain world. The fees we pay to get our transactions recorded and the distributed permanent record, and some interesting differences between the top two cryptocurrencies, Bitcoin and Ethereum. Today, as always, I'm joined by the other host of the show, Stephanie Murphy.
Hi.
Jonathan Mohan.
Hey, hey.
And Andreas M. Antonopoulos.
Hello.
Thanks to all the hosts and to you, the listeners, for sitting in on today's session. So, transaction fees. It's not a sexy topic, but it's a critically important one. Under normal circumstances, it's like putting a stamp on a letter. It's generally quite cheap, and how long it'll take for that $15 worth of Bitcoin or that CryptoKitties token to arrive at its destination is fairly predictable. And to be clear, normal means that the number of transactions being sent is less than the total capacity of whatever blockchain you're using. In that situation, miners are incentivized to take whatever fees they can get and fill up each block with as many transactions as they can. Sometimes even transactions that have incredibly low or even no fees at all get swept along. But all that changes when usage spikes up and miners have to start picking and choosing which transactions will get confirmed quickly and which ones they're willing to wait on. When that happens, senders start to compete for faster service by increasing the amount they're willing to pay, which can spiral upwards in expense as the market struggles to figure out exactly what it's worth to them for that fast service. So we've got a few areas to touch on in today's discussion, but let's start with basics. Andreas, what's the thinking behind this two-phase approach to fees, and what are we trying to accomplish here?
The simple answer here is that there will always be capacity constraints in a blockchain, especially a blockchain that has decentralization as its goal, and therefore needs to keep the resource utilization low enough that many people can participate in either the validation and mining or just the mining of transactions. So in order to do that, you have constraints on how much data can be recorded in the forever immutable blockchain because it has carrying costs. Then the question is, how do you allocate that resource? And the simple answer to that is that there's two ways of allocating that scarce resource, which is the capacity of the blockchain, which is not infinite. One way is a market, an auction, effectively, which is what fees do. And the other way is by authorizing someone to decide what should take priority and what shouldn't. And that second part is often hand-waved, meaning that people assume that it's okay, we can just have free transactions or very, very cheap transactions for everything. But if you really do have a resource constraint, which you do if you're trying to keep things decentralized, eventually you're going to have applications being developed that try to use that for different purposes. And then if someone has to decide, the power to decide which applications are worth transmitting and which applications are not worth transmitting is a pretty important power. It effectively leads, in my opinion, to a dictatorship of the developers. They get to say, this is spam, this is real, this is useful, this is not. A market-based approach says that the best mechanism for allocating scarce resources is a market. And by having a fee auction, the sender of a transaction can tell the market how much they value the prioritization of their transaction from their own perspective and make that choice. If it's not important to them, they can put a low fee. If it's very important, they can put a high fee. But nobody gets to tell them that their application is or isn't important.
You know, this reminds me of, I believe it was like the original invention of proof of work, where it was a solution to email spam, because there was some problem where people were sending out email spam. And, you know, was it Adam Back who was inventing this?
That's right.
Hashcash.
Hashcash, exactly. Okay, so Hashcash was meant to basically prove that you are a human being whose computer is doing work in order to send out an email, in order to prove that it's not just a spam transaction and there's a cost to sending an email, or at least if you want to prove that it's a legit email, there's a cost to it. Instead of, you know, at the same time, Congress was trying to make laws about what is spam, and you have to have a physical address in order to send out email newsletters and stuff like that. And they had the Canned Spam Act, but Hashcash was a market solution to the very same problem.
Yes, and ultimately that is really the choice. In fact, in most of this debate, the idea of this being magically resolved through decisions being made elsewhere is the problem. Because if you don't have a market, all other choices that you make create some kind of centralization of power. You can't get around the fact that there is a scarce resource. And if you increase or if you distribute that resource too liberally, if you create a very big supply of that resource, you're just shifting the problem to a decentralization problem. If you make gigablocks, you can achieve very, very low fees, almost zero or perhaps even zero. But the problem is then you're just shifting the carrying cost to miners and validating nodes and making it so that it is so expensive to validate a transaction and a blockchain that fewer and fewer people can do it, which centralizes power in the hands of those people. So if you replace the market with alternative solutions, basically you try to do some kind of centralized, directed management of this problem, you don't replace the problem. The problem doesn't go away. You just shift it into some other form of centralization.
I want to draw us back from kind of the blockchain portion of this conversation for a second, because I think that there actually really is a real world analog that demonstrates that this is a critical problem that even when you have those sort of authoritative types of solutions, doesn't work very well. I think we're all probably at this point, and many of our listeners, common with this idea of robocalling, right? Where in some cases, certainly for me, the vast majority of the phone calls that I get to my various numbers are not real people. They are essentially companies that are illegally marketing to me. And it is against the law and has been against the law for some time. But from a system standpoint, there's no real mechanism to stop this. So it doesn't matter that it's against the law because the enforcement is kind of like, it requires a lot of work on the person who is the victim of it in order to actually make anything happen. And the cost to actually do it, I put together a proposal a year or two ago about adding a cost to this. And I figured out that to robocall all of Seattle twice, it would be something like $200.
Wow.
And so again, it's an example of like there is an economic cost there, but it's so low that it doesn't accomplish the purpose of keeping the network clean. And in fact, there really is no meaningful solution without completely reworking the way that we do phone calls in order to solve that problem. So, I mean, that's not a blockchain example, but I think it's another example of why using market-based solutions or some kind of solution that doesn't rely on it just being against the law is very important, even in centralized systems.
I have a solution.
Please.
It's called Do Not Disturb. I turned it on in 2013. It's still on.
I know, right? But that's my point is like, I still pay for 3 phone lines, but I don't pick up the phone anymore.
Yeah, that's the thing. It's been completely ruined. I mean, the Do Not Disturb that I have is turning my ringer off.
Right, exactly.
Yeah, exactly. That's the solution. You turn your ringer off. You no longer allow people to asynchronously interrupt your time.
Oh, I thought you were talking about the government do not call list.
No, I'm talking about turning my ringer off in 2013 and leaving it off.
Yeah, right. Same here. I mean, that's because everyone knows that this do not call list is useless and it doesn't work.
Which is why the world now uses Zoom calls instead of phone calls, because who picks up the phone anymore?
But also, what kind of freak would call you rather than Signal voice message you?
Right.
That's my new human check in crypto, is if you want to reach me, just call me through Signal. I immediately know the difference between a bot and a human, and it's because, oh wow, use the most basic form of encryption, and all of a sudden you get back to meat space related interactions again.
Yeah, what this really demonstrates is that you can't replace economic incentives with regulation, and you most certainly can't negate real economic incentives and costs with even more regulation. And in the case of a fee market, that's exactly the issue, which is that you have to regulate the allocation of the scarce resources. And you can either do it with economic incentives and marketplaces, or you can pretend that the economic incentives don't exist and try to regulate a solution that is kind of compatible, and it will always be inferior and transfer power to those who have the regulatory capacity. Or you can go even further and try to negate the economic reality with regulation, and then you end up with a system that gives even more power to regulators and ultimately doesn't solve the underlying problem. The problem being that it costs $200 to spam all of Seattle, or that you transfer power to miners and reduce the number of validating nodes if you allow for very, very large blocks.
But then when you get to regulating your system, it comes down to what are you prefacing and what are you trying to dissuade? and what are you incentivizing and what are you disincentivizing. And it's not always so clear cut, or even comes down to like a moral category of, well, gigabit blocks would preclude the little guy. It really then comes down to philosophy about your network and what specifically you're trying to engage with and promote.
Yes. And, I think that's a valuable discussion to have. It's a valuable discussion to have about what are the principles and what are you aiming to achieve, and therefore which side of these design trade-offs do you want to fall on? How do you want these optimizations to trade off various principles? The problem I have is that very often this is couched in a way that there are no design trade-offs, that you can have your cake and eat it too, that there is such a thing as a free lunch, that either resources are unlimited or economic incentives don't actually apply.
Well, can't we just pull an Ethereum and say that gas fees are really bad right now and call that gas fees 1.0, and then give a really good name to gas fees 2.0? Like, let's say, I don't know, something that rhymes with Casper, and then call that gas fees 2.0, and then put all of the non-feature complete solutions that have no trade-offs in that gas fee 2.0 solution, as we ultimately never arrive to receiving gas fee 2.0.
Oh, then you'd just be full of gas. I mean...
or full of ether.
Okay, so talking about fees, I mean, like, again, this is not a problem. Jonathan specifically bringing up that Ethereum is having a problem with fees at the moment, or was until recently. I think drawing back from that, this is a problem that's affected any blockchain that's actually gotten sufficiently popular enough to kind of overcome that capacity limit, right? In terms of once you have more transactions coming in or more activity on a blockchain than a blockchain can support during that same amount of time, then you have a problem that basically escalates until people are kind of forced to choose not to transact because the cost of doing a transaction, the cost of interacting with the blockchain is too expensive for them. Now, I think that there's a valid conversation to be had there about whether or not that's a desirable feature of blockchains. But I think to Andreas's point, I don't actually think there's another way to do it. Like, all of the other alternatives seem like they're kind of worse in a lot of ways.
It depends on what you're trying to achieve. I think the thing that we're missing yet from this conversation is that when what you're talking about is akin to the post office, send a letter, right? And do you want to pay UPS Express, or are you willing to just go first class, or do you want, donkey mail, the cheapest possible, eventual possible delivery, maybe not? That's a fine conversation to have. The side effect of fee markets, and this is where things get tricky, is when you have things that absolutely must be delivered because there is a deadline. Let's use a ridiculously out of this world example. Let's say you have an election and someone's trying to mess the post office up so that people can't actually deliver the mail on a very specific deadline, which is when you need to count the votes. Now, in this ridiculous example, you can't solve that with a fee market, because then you've created a situation whereby something that should have guaranteed execution now is dependent on whether you can afford the fee at the time. And sometimes you can't change the fee. Now, this applies in very obvious cases in both Ethereum and Bitcoin when you start talking about second layer protocols or smart contract execution. And we've seen this happen in two areas. It becomes a problem for fee markets. One is Lightning Network. Let's say you have a commitment transaction that allows you to effectively broadcast a penalty if the other party tries to cheat. Well, you have a specific period of time in which you need to broadcast that penalty. There's a timeout mechanism, right? If you don't broadcast your penalty transaction within that time frame, the other party gets to steal your channel balance or part of your channel balance. And so the game theory, the mechanism of Lightning depends on your ability to send that penalty transaction. But the way it is today, you have to calculate the fees in advance. Well, what if when the time comes and you need to send that penalty transaction, fees on the network are out of whack? That's problem number one. You can't recalculate the fee because that requires changing the transaction. The second problem, of course, is that even if you can recalculate the fees and increase the fee of that penalty transaction through some mechanism, in Lightning that would be a thing called anchor payments, which is essentially child pays for parent, then you now have a very difficult game theory situation. What if the fees that you have to pay to get this penalty transaction in are more than the penalty that you're going to earn, more than the reward you get from penalizing the other party, well, then it's not worth doing. So you end up losing after all. And of course, you might not be able to reach any amount of fee that gets that transaction in. The backlog may be so huge that no matter what you try to do, you can't really do it. So that's one situation. The other situation similar in Ethereum was, again, deadline based. So during the big crash in March, where the price of all cryptocurrencies, well, almost all, dropped by anywhere from 40 to 60%, a bunch of DAI collateralized loans became under collateralized. Now, that means those loans go to auction if they're not recollateralized as quickly as possible. So you have a very short window of time, less than a day, to recollateralize those loans before they go into a secondary market auction and get auctioned off. And in this particular case, the gas fees exploded at the same time that all of these loans became under collateralized. And even though people were ready and willing and they had ETH available to recollateralize these loans, they couldn't get their transactions through. And so their loans went to the secondary market to get liquidated. About $5.5 million lost. And I don't know if they ended up getting refunded.
They did not.
They did not, right? They took a vote not to.
That's right, yeah. The original thought was, and I believe there was an initial vote that suggested that they would actually be compensated for those losses. But my understanding is that in the final vote, it did not wind up that way. And that just wound up being losses that were eaten by the people who were affected by it.
Right. So that's another example whereby there are some problems with the fee market approach, or some side effects of a fee market approach, where if you have a fee market and you don't have a mechanism to prioritize certain must-do transactions, then that fee market can result in failures.
Is that really a problem with the fee market approach, or is that simply that there was, again, even in a fee market approach, so much competition to have one of those transactions that actually does happen during this incredibly busy time when so many people are seeking to use the network?
Yes.
Is that a failure of the fee market, or is that just a reality of the fee market, that fee markets necessarily have winners and losers?
Well, I would even go one step further and say that fee market or not, blockchains aren't order books. I think we keep running up on this constraint of let's entirely adapt the fundamentals of finance that are predicated on an order book, on a system that batches transactions, not utilizing atomic ordering. And so when breaks, it only breaks when everything is breaking. And so everything seems optimistic until one black swan occurs. And it's only when a black swan occurs that everything catastrophically fails, because it's not an order book. It's a batching system. And, you know, it's sort of like the early days of Amazon, where people were just pushing their server to Amazon and then saying, this is not cheaper, I have no idea what's going on. They had to fundamentally re-architect their design to optimally use Amazon Cloud. And then now people understand inherently how to architect to that. If you're building a system because you're lazy, and most of the thinking in Ethereum dApps is fundamentally lazy, you can't build a system that requires an order book when shit goes upside down, because that's not Ethereum and that's not Bitcoin.
Right. And so, you know, that's one of the ways to test these systems, is every now and then you do have an event like that and everybody gets to rethink their original design and, of course, also their original risk models. And, you know, how much excess collateralization do you need in a DAI loan with the new assumption being that you can have a 55% price meltdown and gas cost explosion on the same day, which, of course, they're going to happen on the same day. So when it rains, it pours in blockchains, and that's when these models are strongly tested. But there's some very interesting work happening as a result of this, including to how fee markets are structured. So far, we've talked about an auction model. It's a weird type of auction, though, because it's a blind auction and you're operating in retrospect. So you can only see the bids that you can see at the moment, but there are other secret bids that you haven't seen yet. And the auction runs continuously until some arbitrary moment in time when suddenly all of the bids are executed. So it's a very weird kind of auction. And a lot of wallets have a lot of difficulty dealing with this. You have no way of knowing what the minimum fee will be to get into this block, or the next several blocks, you can't predict. And it's a feedback loop whereby if you pay more in order to get in, you're also changing the market, causing others to pay more in order to get in. And that ends up being a race to the top.
I guess this also comes down to a broader topic in relation to system design when it comes to variance. It's sort of like a variance is a game of hot potato, and you have to decide in your system at all times who's the one holding it and for how long. And it seems that even more so in Ethereum than Bitcoin, that being able to predictably understand how much executing a transaction shall cost has enormous variance from time to time. And, as the system scales and as it potentially has more users than people who bake bread, is how much of that system variance should we maintain that the individual user should continue having as they interact with anything in Ethereum? When we're talking about, in the postal service, I could be mailing a letter, God forbid I would ever do so, from the northern part of Manhattan to the southern part of Manhattan. And let's say stamps cost 40 cents. That would cost me 40 cents. But America's decided that the same person mailing the same letter from Alaska also costs 40 cents. So I think that, when we look at transaction fees, especially in Ethereum, there's some real conversations to be had about, user variance, both in terms of time and order, but also just in terms of cost and predictability. We talk about mining pools aggregating in order to lower like these tiny, tiny amounts of variance. And yet we're very far behind in lowering variance when it comes to the user's experience in transaction fees.
So we've talked about how to handle fees and just these problems of allocating resources on a network, like a cryptocurrency network broadly. But let's get more specific and talk about the two best, maybe known or most used cryptocurrencies, Bitcoin and Ethereum, which have very different ways of handling this problem of fees and resource allocation. So with Bitcoin, it's pretty straightforward. You're sending a transaction and you attach a fee to it in Bitcoin. Ethereum has this thing called gas. Now, what is gas? How does it work? And they're even talking about changing it recently. But let's talk about how it works right now first.
So the fundamental difference between Ethereum and Bitcoin in terms of the fees starts much earlier and has to do with the purpose of fees in the two systems. And it goes back to the fact that Bitcoin is not Turing complete and Ethereum is Turing complete. Turing complete means that it can do arbitrary computation, and that arbitrary computation can go into infinite loops and last forever. That's a very vast simplification, of course. And you can't really predict how long something is going to take to execute without basically executing it, at which point it might end up taking forever, to keep it simple. With Bitcoin, the scripting language is not Turing complete, so you can actually calculate exactly how long it's going to take to execute, and it has a maximum limit on how many signature operations or SIGOPs it can execute in a script. That is rarely reached. It's a very, very big limit, and it's irrelevant for the vast majority of purposes, which means that transaction fees in Bitcoin are really for the effort of mining, not the effort of validation. Most transactions validate in more or less the same amount of time, and it's not a huge amount of time. With Ethereum, every time you validate a transaction, whether you're a miner or not, you have to validate its entire execution path. You have to run the transaction, any smart contracts it calls, the execution of those smart contracts, the changes they make to the data store, retrieving and saving data, et cetera, et cetera, et cetera. And these contracts may call other contracts, which may call other contracts, which may loop. You never know how long that's going to take. The purpose of gas in Ethereum is to make sure that you have an upper limit. So it's there not just to prioritize the inclusion of transactions in a block, it's primarily there to constrain the amount of computation that a validating node has to do by setting a ceiling on it. And that's the maximum amount of gas that you can put in a transaction and the maximum amount of gas that you're willing to spend, which is what you specify when you run a transaction. So if I send an Ethereum transaction, I am specifying within that Ethereum transaction what my maximum amount of gas is and the maximum price I'm willing to pay for that gas. And the price is calculated in gigaway, which is Ether. So gas isn't a currency itself. It's like a pseudo currency that is denominated in Ether with a variable exchange rate. And it's used not to prioritize transactions in the blockchain, but primarily to constrain the amount of computation that has to be done by everyone to validate those transactions by running all of the smart contracts.
Okay, so let me just make sure I understand what you said there, Andreas. So in Bitcoin, there are a limited number of defined things that you can do. And you can take those defined things and you can create combinations of them that may involve some complexity. But ultimately, because there are only a couple of things that you can do, the complexity is limited. And sort of that also means the types of things you can do are limited. You can't have fully functional smart contracts in the same way that you can in a Turing-complete system like Ethereum. But it also makes it kind of much more predictable and much more standardized in terms of what type of activity a miner might actually see and wind up processing.
And every Bitcoin script has a fixed runtime. It doesn't depend on anything else. It will take as much as it needs to take to evaluate that script, depending on how many script commands there are and how many signature operations you do in the script. But that's it. The script can't loop back on itself and start running again, and it won't change how long it runs depending on something that's outside of that script. Whereas in Ethereum, it will. It will run a smart contract that can loop, and the length of that loop may depend on a factor that's completely outside of that transaction that has to do with another transaction that somebody else recently did.
So when we think about this, is it correct in thinking that Bitcoin is a more rigid but predictable system, whereas Ethereum is a more flexible but sort of unpredictable inherently system?
Exactly. And predictability is the basis of the Turing problem, which is whether you can predict the execution length or computation required for a specific program. The Turing theorem says that you can't. If the language is Turing complete, then you can't model with another computer how long it's going to take to execute.
So, and this really speaks to kind of the purposes of what these blockchains are for, where sort of Bitcoin really at its core is attempting to be a kind of money, right? That may have systems built on top of it that add lots of complexity. Ethereum really does want to support that complexity at the base layer so that you don't have to build additional systems on top, which come with their own sets of complexities.
You can't do the interesting things that Ethereum wants to do without allowing open-ended computation. You don't want to do the interesting things that Ethereum wants to do in Bitcoin because you don't want to allow the additional computational complexity. And that's the fundamental design trade-off there. Okay, so if you understand that gas is basically how you meter the amount of computation, then the next step is to understand that every command that you ask the Ethereum machine to run has a specific cost in gas. That's the accounting system. And so if you want to add two numbers together, that costs 2 gas. Let's say I'm just picking numbers randomly here. If you want to do a hash, that costs 200 gas. If you want to store data, that costs 250 gas. If you want to do an elliptic curve multiplication, that costs 2,000 gas. And, proportionally, these are set in advance to make some kind of sense in terms of how that reflects the amount of computation that's required. And they've been tweaked from time to time, both because some things were underestimated and gave opportunities for denial of service, and other things were overestimated and they wanted to make those more appealing. So there's essentially a price list. For every processor command you want to run, there's a price list that tells you how much that costs. And when your smart contract starts running, when your transaction runs a smart contract, the Ethereum virtual machine, wherever the transaction is being validated, basically starts keeping a tab of how much your gas you're spending, keeping an eye on the total amount to see if it exceeds the maximum you've agreed to pay in the transaction. If the system completes successfully, your smart contract runs, you get charged for that gas. Interestingly enough, if your transaction fails, you still get charged for some gas because your transaction is still mined and it produces an error condition or something like that. You still pay some gas, although perhaps not the maximum amount of gas for that transaction. And one interesting wrinkle there, which opens up quite a few possibilities, is that there is one operation that actually has a negative price. And that is the operation of releasing data allocation. So when you record a variable or you store data on the Ethereum blockchain, you have to pay for that. But when you release that data, you actually get a small amount of gas back.
Meaning the gas is released? Sorry.
The gas is released.
Had to get a fart joke in there somewhere.
Yes, exactly.
I mean, it was begging for
it.
It
was. So not to make us think about this, but the bottom line, I couldn't help it. So the bottom line is that because this one operation gives you a credit, which is not going to be enough to make your transaction free, but can reduce the overall cost of a transaction if you're releasing enough data in that transaction, you have some interesting side effects. And that is you can actually have a market for gas that emerges from this process.
Okay, so how do you get a market from gas? Is that because the price of gas is denominated in ether, which fluctuates based on the market prices, and you can sort of bank it when it's cheap and then use it later when it's more expensive?
Exactly. So take a smart contract, for example, that has two functions in it. And one is, let's say, bank gas, and the other one is withdraw gas, right? And what the bank gas does is it allocates an array of 1,000 bytes. So it just goes and allocates and allocates and allocates and allocates 1,000 bytes. And that costs you 200,000 gas because that's 200 times each byte that you allocate. I'm picking numbers out of thin air right now just to make the point. Now, if you do that, if you run that part of the function when gas is really cheap, when the exchange rate of gas to ether is really low, you end up allocating 200,000 units of gas at a very low price. Now, when gas is expensive, you can go and run the other function, and you can run it as part of another contract execution. You can just prefix your contract execution, wrap effectively the smart contract that you want to do, which is something useful, a decentralized exchange, a DeFi project, whatever. You can wrap it with a call that first releases the banked gas that you had, withdraws it. And what that function does is it goes and it releases that memory allocation, giving you a partial gas credit, which then goes towards your overall gas costs for running the other thing you were doing. So let's say you were using it to withdraw some DAI from a smart contract. And normally that would cost you 200,000 gas. But instead, because you first withdraw gas from this banked gas contract, it only costs you 50,000 gas to run this thing because you pay 200,000 to withdraw your DAI, but you get 150,000 credit from releasing the banked gas. And so in practice, it only costs you 50,000 gas. So you've bought gas when it's cheap and you've effectively gotten it back when it's more expensive. And that way you have essentially a gas savings market.
Okay, so like, do people actually do this? Do they create like crap contracts that tie up a lot of gas and then release it later?
Absolutely. Well, they don't create crap contracts that do that because you only need one. So once someone created a contract that was nice enough, simple enough, easy to audit, etc., that did this process and had the ability to bank gas when you need it, when it's cheap, and then release that as part of a bigger execution of contracts when you want to get a credit, well, everybody started using that. There's no reason to do another contract. You can just use the contract that's already there. And it's got a nice API, and it's very easy to write smart contracts that include this in their execution. And this is used in a number of different smart contracts to save on gas.
Right. And this comes back to like system philosophy, which is whether or not you think this is a good thing or a bad thing. Because, the reduction in variance on gas prices well then means that by definition, you're lowering the upper variance and the lower variance, which one way to look at it would be great. We're creating certainty in Ethereum gas, at least increasing it. And on the other side is saying those evil capitalists, they're increasing the base fee of Ethereum writ large, and we need to do something about it.
Let me make sure I understand exactly what's happening here in terms of like practical real world impact, right? So if a transaction that I know I'm going to make in the future, it costs $2 today, but it might cost $20, the day that I want to execute it.
You have the perception of it costing $20 in the future, or the anticipation of it potentially costing $20.
Right, exactly. Like I know that there are transactions that I'm going to want to make during a time when it's high volume. The currently blocks are not full, and I can get an equivalent amount of data into the blockchain for like $2. So effectively, I do that. I pay the $2 now. And then at the later point, when I'm getting rid of this data that I've put in, but transactions cost $20, I'm actually getting $10 worth of value back in terms of that rebate. So I've had a gain there effectively of about $9 for the $1 I wound up actually paying.
To think about it in the most real world examples, it's sort of like deliverable futures in the commodities market.
Yeah, it's a futures market.
Right. But deliverable futures, where you run a trucking company and you just need to lock in the price of diesel. And it doesn't matter if you're paying a slight premium for it. You need to lock it in because you just need to know what your margins are going to be for the next 6 months, for the next 2 quarters or whatever. And that's what you need to do in order to run a commercial enterprise. Now, someone could look at that and say, that's fantastic. This guy's able to run his company effectively. Another person could look at it and say, that dirty mo increasing the market price of gas and his anticipation of the price going up into the purchasing and locking down of these futures is in and of itself what's increasing the price of gas itself.
Evil speculators are messing with the market. Yes, you get that kind of effect. It's a secondary effect of this market. Your anticipation that the price will go up actually does cause the price to go up because other people can see that bid you're making and are probably trading against those futures in the opposite direction if they don't think it is going to go up, or in the same direction if they think it is. And so you've effectively created a secondary market, which then people start doing naked speculation, not because they're trying to hedge the price of diesel for their trucking company, but because they're trying to make a buck off other people hedging the price of diesel for their actual trucking company. And in some cases are artificially increasing the price of diesel. So yes, that's exactly what happens. Interestingly, there's a new proposal now to change even more radically the way the gas market works by effectively dynamically adjusting the price of gas by burning it and not giving it to miners, which is a proposal called EIP 1559, which is getting a lot of attention now. I don't know what the status is in terms of its implementation. I think it's still a proposal and in draft state, but it's quite vigorously pursued right now, and there's a lot of interest in it.
So the point of this proposal would be to stabilize the price of gas so that it really doesn't have these fluctuations that can be harvested later?
Yes, it's basically suggesting a change that effectively changes the way gas is used to change the incentive mechanisms in this market so that it's not a first price auction mechanism where you have to bid the maximum fee and the miners get the difference, because that encourages, as we've seen on Bitcoin too, the miners to game the system to maximize fees. And that's one of the risks of these first type auction systems, is that you have a ringer in the auction who's bidding up the price for an item with no intention of buying it, as long as they have a relationship with the seller of that item. And so if they end up accidentally buying it, well, they're buying it from themselves, so it doesn't really matter, right? So this is the problem with auctions. In the transaction fee space, what that is miners putting transactions onto the blockchain to drive up the transaction fee, knowing that if they have a sufficiently large hash rate, they're going to get that money back from themselves. And even if they don't, as long as all of them are doing it, they're getting other people's fees while other people are getting their fees, so it's all a wash.
Andreas, I'm pretty confident that in Iceland, that's just called banking.
I'm pretty confident that in all other markets, that's called a cartel. And this is a well-known problem. So basically here are the stated goals and motivation for EIP 1559. So the first one is to fix the mismatch between the volatility of transaction fee levels and the social cost of transactions. Basically, the fact that this volatility creates a bunch of inefficiencies in the system because it forces people to overbid and bank gas and all of that. Delaying transactions for users, so needless delays. Inefficiencies in the auction mechanism and instabilities of blockchains that have no block reward. So basically, transitioning to fees only and having a possible future instability where fees do not adequately subsidize the security cost.
So I'm kind of confused as to the proposal as to why it would get adopted, Because let's just say that Casper doesn't get implemented yet, and we're still in the Ethereum 1 world, which is what the proposal is meant to address. How do the incentives work to get miners to signal to adopt a system that would remove their own transaction fee reward?
The difficulty bomb, I'm assuming. Ethereum has a built-in mechanism that makes mining impossible or increasingly impossible, increasingly too difficult over time, forcing miners to accept a hard fork at regular intervals to diffuse that difficulty bomb and then reset it and then diffuse it again and diffuse it again and diffuse it again.
It's a red line in the sand that every now and then has teeth, but more often than not doesn't.
Right. And the intention here is to not allow miners to take the system hostile and stagnate the introduction of changes by basically cartelizing the blockchain. Now, when it was first proposed, I had a lot of skepticism. Then 2017 happened with Bitcoin. Now I'm thinking it might not have been such a bad idea.
Right. We need a different cartel of people who just own a bunch of ether.
Yes, so it's all a battle of the cartels. Do you want a cartel of developers, a cartel of miners, or a cartel of owners? And what is the relative balance between the three? Because these power dynamics exist in every blockchain, whether you acknowledge them or not, and whether or not they're powerful.
So I can recall an update, and geez, I wish I could pull it off the top of my head right now. There was an uncle rate upgrade that specifically optimized Ethereum transactions and reduced the uncle rate. But because it reduced the uncle rate, it would statistically reduce miners' ability to generate income off of their uncles.
What is an uncle? Is that like an abandoned block or something?
In Bitcoin, mining is first past the post. The miner who finds the block first wins all of the reward, and other miners who may have also found a solution to the proof of work, perhaps a few seconds later, or even before but weren't seen by the network, get nothing. In Ethereum, that's not how it works. The first miner gets a proportion of the reward, but if other miners also submit additional proof of work, those blocks do not get orphaned. Instead, they become siblings of the parent, therefore uncles, that also get a portion of the reward redistributed to them and share in the reward.
Yeah, so the best way to think about it is when millennials make blockchains, they get participation trophies.
Yes.
Another way to think about it is it's like, you know, one winner bingo versus potentially a bingo round that has multiple winners where, you know, the earlier you win, the better the reward is.
This is an alternative consensus algorithm. So if you think the consensus algorithm in Bitcoin is greatest cumulative difficulty chain, right? So the greatest cumulative difficulty chain is the only chain and it wins. The parent that introduces the greatest difficulty ends up winning the chain. The consensus algorithm in Ethereum is called GHOST, G-H-O-S-T. This is why a lot of the future developments are called Casper. And GHOST stands for Greedy Heaviest Observed Subtree. Greedy because we include additional blocks. Heaviest, that's the cumulative difficulty. Observed because it actually happens after the first parent is mined. And subtree because it's not a chain, it's a subtree. And it's an alternative consensus algorithm. It's very interesting to read about how GHOST works, but it does involve this mechanism of uncles. Now, to extend our previous puns, if your uncle is producing too much gas, then you want to change the number of uncles in the room.
And Stephanie, just in case you're wondering, the reason why it's called an uncle rate and not an auntie rate is if it was an auntie rate, there'd be way less abandonment in the system.
Well, in fact, in Ethereum, it's called an omer, which is a gender-neutral term for uncles, because Ethereum is rainbows and unicorns. Jonathan, you should know this.
So when it came to this proposal that optimized transactions and reduced the uncle rate, now I haven't checked in it for a while. I'm sure it eventually got passed. But miners were like, oh, you're proposing something that's going to knowingly reduce the amount of reward that we get in the system. Even if it makes the system more efficient, that doesn't really sound like something in our best interest to activate. And so we look at, blockchains being systems of economic incentive. It's really interesting to see how you can implement an update that services one context of the ecosystem to the detriment of the party that ultimately approves or votes for the things to get implemented, which are the miners.
Yeah, I mean, it's a battle, right? It's a battle of interests.
I mean, when I look at this proposal, it sounds intelligent. I look at it, it makes sense. I can't help think about, I'm like, how does that conversation actually go? Because I've worked with miners, I've conversed with them, I know how they think. It's sort of like that scene from The Dark Knight where the Joker just gets them in a room with like a couple $100 million and sets it on fire and is like, welcome to the new world, just deal with it. Like, how exactly does that conversation go down?
Well, pretty much like that, because ultimately the money in the middle of the room is the miners' invested capital in GPUs, and Vitalik has always stood by with a lighter. We're going to burn all of that invested capital and switch to proof of stake anyway, so that's that. It's a very specific and very deliberate kind of standoff where Vitalik from the very beginning did not want miners in Ethereum to have the same amount of power that they do in Bitcoin, and chose to make some very different choices. Since we've done all of these parent-child-uncle relationships, I just want to point out that Polkadot's consensus algorithm, which was built after Ethereum's, obviously, by Gav Wood, is called Grandpa. And Grandpa stands for Ghost-Based Recursive Ancestor Deriving Prefix Agreement.
Wow.
Nerds everywhere.
Nerds everywhere. More acronyms that are actually backronyms. Yeah, I think it's funny. But they actually mean something interesting and do tell you a few things about the properties of the system. All right, so let me go back to EIP 1559, because the basic idea here is that there is a base fee per gas, which can move up and down each block according to a formula, which is a function of how much gas was used in the parent block and the gas limit. Basically, it's like applying a difficulty retargeting algorithm, but to gas instead of difficulty. So in this proposal, EIP 1559, gas goes up and down dynamically, but based on an algorithm that accounts for supply and demand. And in order to prevent the miners from gaming the system, the base gas is not given to miners, but instead is burned. And there is an additional amount of gas on top of the base fee that is a tip to miners, which is not considered in the prioritization of a transaction. So this essentially disconnects the incentives that miners have to game the system, and it engineers the fee market so that the fees cannot vary as much between blocks. They have a maximum adjustment between blocks, and that's to tamp down volatility. But effectively what it's done is it's introduced an algorithmic solution in place of an auction-based market. What are the side effects of that? How does the game theory play out? Well, we'll find out when real money is on the table with real actors with interests and incentives competing for that money. So you can't really test these systems on paper until you put the money on the table and everybody tries to grab for it.
Yeah, that's the thing about Ethereum. Like everything is a giant experiment, and that's exciting, but it's also not very stable sometimes.
I mean, that's the thing about this whole industry, right? It's not just Ethereum.
Yes, these are real-world game theoretic systems that require adversarial execution. You need to run them with real money, with real adversaries, and see what happens. And nobody knows in advance exactly what's happened. Look at the early writings of Satoshi Nakamoto. There was no certainty that this was going to work by any of the people involved, not least of them Satoshi Nakamoto. Everybody said, well, we'll see. This might work. Let's see how it plays out. And I think the primary philosophical difference between Ethereum and Bitcoin is not whether it's an experiment or not. I think on both sides, there's a recognition that it's an experiment. The difference is the amount of conservatism in pursuing that experiment and how many things can be broken, and sometimes broken on purpose, in order to move to the next state of the experiment. And in Ethereum, the culture is very much more progressive in terms of breaking things. And in Bitcoin, it very much isn't. And that's great for a system of sound money, not for a system of smart contracts, and vice versa.
Yeah, definitely. That's a fair point. I mean, it's all experimental, but I don't know. There's just something about Ethereum to me that just exemplifies this, because we see it happen often where things are being tested in the field, in the wild, and sometimes they break, and it's interesting to watch. So does this proposed Ethereum improvement rely on a smart contract too, or does it rely on a hard fork, or what?
Well, specifically, they're burning the change. They're not actually giving it to anyone.
So I think this is a hard fork change that involves a smart contract, but is not implemented solely by a smart contract. It's a fairly big change to how the mining mechanism works, so I don't think it can be done solely by introducing a smart contract.
I think we'll all be interested to see kind of how this works out. It seems like another attempt at the brave new world of these kind of fee markets and trying to figure out how to make these systems really work in real life in ways that are both kind of fair and actually sustainable over the medium term, because they seem oftentimes to be ideas that are at odds with each other.
Yeah, in the end, it's important to keep in mind that this isn't about making something that doesn't break. It's about making something that breaks in different ways.
One of these days, we're going to do a short episode, but that's all the time that we have for this episode of Speaking of Bitcoin. Thank you very much for listening. Today's show featured Stephanie Murphy, Jonathan Mohan, Andreas M. Antonopoulos, and myself, Adam B. Levine. This episode featured music by Jared Rubens and was edited by Jonas. Have any questions or comments? Send me an email at adam@ltbshow.com. And if you enjoyed the show, tell your friends or leave us a review. And we'll see you next time.